Okay, so yeah, good morning, good afternoon, everybody. Hello, everyone. Thank you, everyone, for joining us today for our new webinar, Understanding Industrial Insulation Thickness Optimization and Trying to Improve the Energy Efficiency, which is right now quite a big topic globally. So let me introduce myself. My name is Damian Kumorkiewicz. I'm Technical Sales Manager in Berenberg, former known as Berenberg Solutions. I'm working here for over 5 years. Berenberg's division in Berenberg. It's a leading insulation and a removable passive fire protection solution provider for oil and gas, construction, and infrastructure applications. I'm going to be the moderator today for this webinar. Before I will hand over the presentation to my colleague Adrian Christenhaland, I would like to go through a few basics. So first of all, after the webinar, we will hold 15 minutes Q&A session. So if you have any questions related to the presentation, you can submit all the questions through the Q&A buttons that you can see at the bottom of your screen. The second thing, the webinar is fully recorded. And the third thing, it's during the Q&A session, we will launch the short survey. So that, with a few questions, therefore, we would really appreciate your responses stated in that survey. Okay, so that's it from my side. So let's get started the webinar. So right now, Adam, it's your part.
Thank you, Damian. My name is Adrian. I am the engineering manager for our product portfolio in Berenberg. And today's topic is energy efficiency and insulation optimization. It's a topic that's perhaps become even more important than it used to be. A short look at the agenda for today's webinar. First, we will go through the background and introduction, the basics of insulation. So I will take a brief look on why we insulate and where we can apply energy optimization. Then we have a brief look on the recent changes in energy market and energy prices. And we will go into the process facility and have a look at different approaches to improving energy savings and reduce energy cost. Then we come into the core of today's webinar, which is the economical optimization of insulation thickness and insulation solutions. How can we achieve the most insulation performance for the same amount of money? Then we will, in the last half of the webinar, present a case study and show how this have been done in real-life projects and how we helped a big refinery operator, Lotte Chemicals in South Korea, to reduce their energy cost and CO2 emissions. At the end of the webinar, we will have a Q&A session. At the same time, as Damian mentioned, we will launch a poll. So enjoy. So the basics, why do we insulate? There are several different insulation classes today, and not all of them are relevant for insulation optimization and energy efficiency. So which insulation classes can we actually apply energy optimization and thickness calculations for? Well, in order to save energy, we have to be sure that a unit of saved energy can be translated into a unit of saved cost. So it doesn't make sense to insulate other insulation classes in terms of energy optimization if we do not know that the unit of saved heat will actually be contributing to saved cost down the line. I will come back to this. Now, the insulation classes that we focus on in this webinar will be class 1, 2, and 4. So heat conservation, cold conservation, and frost protection. These are usually the insulation classes where we see a tight connection between saving energy and saving cost for operators. And this is where thickness optimization comes in. So why did we choose this topic for today's webinar? Well, the reason is the rapid change in energy markets. During the last couple of years, we have seen an explosion in energy prices, gas prices, electricity prices, and the price for CO2 emission quotas. This means that heating and heat waste have become more costly. Electricity consumption in terms of heat tracing, etc., have become more costly. And the cost of burning fuel to heat processes in terms of using hydrocarbon fuel have also carried a larger cost now than what it used to do a couple of years ago. So what's our baseline? Well, if we are building a new office or house today, in many cases you are required by law to have a minimum of 250 to 400 millimeter for insulation to meet the local building regulatory standards. But in the oil and gas industry, on many facilities, we are still using the same thickness tables and insulation systems that we did 40 and 50 years ago. So it means that for 50 degree, 100 degree, 150 degree, in some cases even 200 degree Celsius pipelines, we are still insulating them with as little as 50 or 40 millimeters of, for example, mineral wool or cellular glass or perlite or what have you. So there is a large gap to fill. And why have been using so low insulation thicknesses historically? Well, the main reason is that for a long time, many oil and gas operators have had access to either very cheap energy in the sense that they can use gas from the oil field, or they can use byproducts from the refining process as fuel. And if this is products that they haven't been able to sell or achieve a high price for, energy has been very cheap. And also, as we know, the lifetime of insulation can be quite short compared to a building or a house. So what are the different strategies we can use to optimize insulation? Well, there are two approaches we can use. One is to look in existing plants, for example, by using drone technologies to inspect for by infrared camera to detect heat bridges and faulty insulation. And the other is thickness optimalization and energy efficiency calculations when we applied new build. So when we have the chance to insulate new equipment. I will show some examples here. And these are not special examples. You will find not hundreds, but thousands of examples like this in a common refinery facility, almost anywhere in the world. You will find heat bridges on supports, uninsulated supports. You will find uninsulated trunnions. You will find wet insulation, and you will find even poorly insulated equipment. Some of the time this has been done by purpose because the customer wants to inspect the equipment. Some of the time it's done by accident, for example, as a result of damages or wet insulation. And some of the time the client is simply not aware of the cost of the heat loss. Now, for 30, 40, 50 years, this has not been a problem because the cost of energy has been relatively low. The access to energy produced by themselves from the operator side have been readily and quite widely abundant. And also the cost for CO2 emissions from burning fuel in order to drive heating have been relatively low. But what are the costs of some of these examples here today when we consider today's energy prices? How much does a heat loss for a support or a trunnion or wet insulation cost to operators in terms of energy bill, in terms of CO2 quotas, and in terms of electricity consumption? Due to the recent energy prices, cases like these now cost the operators almost unimaginable amount of money, because this is not a special example. you will find hundreds and thousands of these examples throughout the refinery plant. But let's say we cannot run around the plant and change all that was done yesterday. Where can we have an impact? The biggest impact we can have today is when we insulate new equipment. And this is where we can apply energy and thickness optimalization. But in order to conduct calculations like this, we need to know a few input factors, key factors and assumptions that will be used for the calculation to give the results that we want. We need to know what the cost of the insulation is. We need to know the cost of the installation. So how much does it cost of scaffolding, man hours, cladding materials, surface treatment of the equipment, etc. We need to know roughly the lifetime expectancy of the equipment and the insulation materials that we are using. We need to know the operating conditions, and we need to know the process condition. Now, the process condition is perhaps the single most important factor, because we need to know that we are insulating and optimizing an insulation system on an object where saved energy will actually translate into saved cost. Now, many does not know this, but in many refineries and petrochemical plants, for large parts of the process, saving heat will not save money. In many parts of the process, heat is an unwanted byproduct. And in some parts of the process, you even have to cool down the process line for the next reaction or chemical transition to take place. So it's only on parts of the oil and gas facility that you will actually have economical benefit from insulating more. And this is the area where we should focus insulation optimization. Not everywhere, but where it will save costs and emissions. Last but not least, we need to know the energy cost. So what's the operator paying in terms of euros per kilowatt hour or per fuel, and what's the CO2 cost? What's the CO2 emission and what's the CO2 cost in terms of emission quotas? When we know all of these factors, we can start running the thermodynamic calculations and heat transfer calculations. So we use advanced calculation modules to calculate the heat loss for different insulation materials for different insulation thicknesses. It would look something like this, where you input geometrical data, boundary conditions, you input material data, thicknesses, and climatic conditions. And you will calculate for each thickness, for each material, for each line, a heat loss, watt per meter, or in case of vessels, watt per square meter. Using the energy price, we can translate this into a yearly energy bill for that specific piece of equipment. And by calculating different thicknesses and summing up the lifetime and discounting for net present value using an internal rate of discounting, we can establish lifetime operating cost net present values for different insulation thicknesses. The example you see here to the lower right, we calculated for 4 different reactors, reforming reactors at the refinery, and we calculate different insulation thicknesses, in this case of mineral wool, how much the heat loss will cost the operator in terms of lifetime operating cost. So in this way, we can establish operating expenditure or cost of heat loss operating curve. Of course, the more insulation you put on, the lower the cost of in terms of heat loss will be, but you are also putting on a more expensive solution. So you will have a capex component as well. The cost of the insulation, the cost of the scaffolding, the man hours, the cladding material, the insulation material. You have a certain startup cost. The scaffolding is the same, independent of the thickness. You may need to do the recoating, etc., which is a fixed cost. And as you put on more insulation material, you will have a gradually increasing, not necessarily linear, but gradually increasing capex curve. And by summing the OPEX and CAPEX part of the equation, we can establish a total cost curve for the insulation system and plot it out as a function of thickness. So on the left side, we have too little insulation, and you have too high cost in terms of operating expenditure. And on the right side, you have too much insulation. You have a too expensive insulation system where you don't need it. In the middle here, we can identify a economical optimal insulation thickness. And this is the thickness that will give the shortest payback time, the most insulation performance for value, and also it will give the lowest life cycle cost for the operator. This is the essence of insulation thickness optimalization. So how does it look in real numbers? We have calculated an example here. We have assumed a 10-year lifetime for 8-inch pipe. 10-year because typically we see that insulation normally have to be maintained or replaced after more than 10 years due to water ingress, etc. We have in this case used an aerogel insulation as an example, and we have used the energy cost of 5 cents per kilowatt hour, which is not very high. It's perhaps representative of what used to be before the energy crisis and before the war on Ukraine. So we see, for example, for a 100-degree pipeline, we find a economical optimal aerogel thickness of 30 millimeter, for example. And of course, as we put on higher and higher temperatures, we will need more and more insulation to be in an ideal position. Now, if you plot this out for different insulation material, it will look different. For example, if I use cheaper insulation materials, generally you can put on more insulation thickness because the material is cheaper before you reach the bottom part of the curve. And for more expensive materials, the optimal thickness will be lower. But the interesting part here is what is the consequence when the energy price is not 5 cents on the kilowatt hour, but what happens when it's closer to what the latest price is today? What happens if it's 20 cents per kilowatt hour? For example, if you're using a gas or hydrocarbon fuel or electricity to heat your process. Well, if we compare with the previous graph, you will see that on the left side, the heat loss component has gone through the roof, which is not surprising given that the energy cost has gone through the roof. And it means that yesterday's optimal insulation thicknesses are no longer economically optimal. And it means, as we've shown some example of previously, that the cost of the heat losses we see in today's process facility are quite different from what they used to cost. Insulation system that used to be optimal and cheap in terms of operating expenditure, in terms of operation heat loss, is now costing the operators enormous amount of money. And when we insulate new equipment, we should factor in today's conditions and not use yesterday's insulation thicknesses. So I would like to show a case study from a project we carried out actually before the energy crisis. We initiated the collaborationship with a large refinery plant in South Korea called Lotte Chemicals. It's a large refinery facility that produces everything from gasoline to jet fuel, kerosene, asphalt, plastics, every hydrocarbon product you can think of. And the energy and climate policies in South Korea are quite similar to what we see in the West. They focus on energy savings, they focus on the Paris Agreement, they focus on cutting CO2 expenses, and they have CO2 quota cost quite similar to what we see in Europe. And these policies have led to a number of industry initiatives. Of course, we will focus on the insulation part here, but insulation is also a key component in many of these other areas. If you want to achieve better efficiency on steam systems, on ventilation systems, on waste heat recovery systems, etc., you will need better insulation. Insulation is at the heart of many of these industries. So the first part of the project was what we call the feasibility study. So we want to have a look on the different parts of the plant, and we want to identify the pieces of equipment where energy heat loss is costing the operators large and significant amounts of money. So we had a survey together with a client where we collaborated with a process discipline and reviewed different parts of the process, identifying those reactors, those vessels, those heat exchangers where heat loss was contributing a significant amount of cost. When we've done this, we established the MTO for the project, the pipelines, the temperatures, the quantities, and we start calculating. So we start the calculation that we showed earlier today, and we calculate different materials, different thicknesses, factoring in heat loss and climatic data as well. The materials they use in South Korea are slightly different from what we use in Europe. Instead of mineral wool and cellular glass, they use a lot of perlite. This is the cheap standard material of choice that you will find in a lot of industry. But they also, to a larger and larger extent, are using aerogel products. On very high temperature, they're using something called microporous, which is a more expensive specialty product for the high temperature application. So we go through the entire MTO, the entire scope of work, and we calculate what is the cheapest lifetime cost material for each item, for each pipeline, for each vessel, for each flange, etc. The results will vary based on what you put into the calculations. In this year, we only looked on a 5-year lifetime. So if you had looked at a 10 or 20-year lifetime, the answer would be different. But they had a lot of issues with CY at the plant, and they know that it's better to assume a little bit too short lifetime and than to pay too much for the insulation system and put on a very conservative solution. So we used a conservative 5-year lifetime assumption. And we saw some general trends. We saw that aerogel insulation typically came out more cost effective on the low pipe and low temperature scenarios. We saw that for the very big pipes, 30-inch plus, traditional insulation, in this case perlite, was cheaper, simply because the volume is so large that the insulation cost is the key cost driver. And we saw that for the very high temperature, low dimension piping, microporous came out best. Then, when we establish the right material to use, we start calculating the lifetime cost, capex and opex, for different thicknesses. So we have these large spreadsheets. We try every different insulation material, every different insulation thickness for every piece of equipment. So of course there's a tremendous amount of factors and variables playing around, but this is all happening back-end in the Excel sheets. So it's quite quick calculation, even though there are incredible amounts of variables. And we look on the 5-year lifetime, what will be the operating expenditure and what will be the capex up front. And in total, what will be the cheapest. We plot this out so you can see the development over time. Here you can see an example for one piece of equipment where yes, you might have a little bit higher insulation thickness than the performance that was historically. So instead of using aerogel to match the performance of the perlite, so thinner thickness, we choose to put on a little bit more aerogel so that we can actually, for one, reuse the same cladding because the dimension is actually the same. So we contribute to the reusability of the cladding system. but we also see that on a short time horizon as 5 years, even after 5 years, we have paid back the extra capex expense up front. Of course, the management at Lotte Chemical are concerned with the financial figures. Why should they put on more and more expensive insulation? Why should they invest in more energy efficient insulation materials? So we compare the increasing cost by improving insulation performance, only the increase, and we calculate the saved OPEX in terms of operating expenditure. So in terms of energy bills, electricity consumption, and in terms of CO2 emissions. And we calculate the payback time based on the choice of improvement, if you want. In this case, we saw something between 3 and 5 years payback time, typically. But when selecting the optimized thickness, payback times as short as 2 years appeared in many cases. And it makes sense because we know that 80 to 90% of the cost in many cases is surface preparation, scaffolding, man hours, cladding materials, and insulation boxes. So the incremental cost, the extra cost of a layer extra of insulation is often very low in the big scope of things. It's a very short payback time for adding an extra insulation layer. Here you see some pictures. This was one of the equipment we insulated. It was a very large heat exchanger used to distribute heat throughout the steam generation system on the plant. And as you can see, we used approximately 40 millimeter of aerogel here, 20 plus 20. The last part of the project, we wanted to see how does the calculation match reality. The calculations they're fancy, they're promising big numbers and savings, but we want to measure how does the estimated savings compare to the real life savings before and after we improve the insulation system. So we thermocoupled 6 different pipelines, which were insulated both with traditional insulation and with optimized insulation. And we calculate based on the temperature drop on the medium inside the pipeline, the heat loss occurring on each part of the pipe segment. And we compare this to the calculation to check how well does the spreadsheets and the Excel calculation match reality. It varied a little bit from line to line, but in general we saw accuracy between 92 and 99%. So as we like to say, it's better to be approximately correct than exactly wrong. Don't be afraid to do these calculations, because compared to the historic thicknesses and schemes, you will improve the economical performance of the plant quite significantly. So a quick summary before we go to the question and answer session. The most important point I would say is clearly identify which process benefit from energy savings and heat loss savings. Identify the processes which are driving and determining the energy bill of the plant. And next point, don't blindly copy old insulation tables. They are calculated under different economical circumstances. The energy prices are not the same today. The economical optimal thicknesses of yesterday are no longer reasonable. And last but not least, don't be afraid to do the calculation. It's better to be approximately correct than to trust the old specs and be exactly wrong. So I will hand over to Damien, who will be reading up the question and answers. And at the same time, we would launch the polls. We greatly appreciate if we could spare a few seconds to give feedback on some questions. And please ask any answer and question, that comment, whatever you want in the chat.
Yeah, thank you very much, Adrian. Thank you very much, Adrian, for your time here. So yeah, let me just recall the first question. The first question we received from one of the participants. So are insulation thickness tables adapted to the insulation material commercial thickness available in terms of the temperature range columns in the table?
Yes, very often the thickness table are divided into the thicknesses actually available from the manufacturers. So if the material is available in, for example, 1-inch steps or it's a 10mm steps, this will normally be shown and reflected in the insulation table as well. It's very rare to see insulation tables with 24.5mm thickness. It's often adjusted according to the vendor. But the price and the economical consideration is often outdated. And yeah, I think that's what we've shown in the webinar today.
Okay, thank you very much. I have a few other questions. One of the question which comes to my mind, it's what are typical objects that we insulate to save the money from insulation thickness optimization perspective, based on your webinar case you just presented us today.
Yeah, so there are some common equipment that we see large savings in, and it's typically on actually more so in refineries than upstream facilities, because refineries use a lot of high temperature processes. So everywhere where you see crackers, reformers, heat exchangers, large furnaces on site, that's typically the areas where insulation thickness optimization will give a very large saving compared to the investment. And it's those areas where the topic of today will save the operators the most amount of money.
Okay, and the next questions, what are typical lifetime of the insulation that you are showing us today, as per your experience?
So typically for traditional insulation that over time is subjected to water under insulation and often in many cases have to be removed because of CI. So for example, mineral wool, cellular glass, perlite, calcium silicates, typically everything from 5 to 15 years. Yeah, if they last more than 10 years and the operator is still comfortable with them, you are lucky. Most of the time the cladding will be damaged and water will get in. If you have a water repellent aerogel, maybe you can assume 5 years more, but yeah, it's usually not the insulation material itself that's run out of lifetime. It's usually damages to the insulation and water ingress that destroys the system.
Okay, thank you very much for the response. The third question, how much time does it take to run engineering insulation thickness optimization for the standard refinery? For example, one installation unit like a DCU or coke drum or etc. So
once the scope is identified, the thickness optimization is very quick. It's the formulas are in place in the Excel sheet, so you actually just input the parameters and you get the answer out. So the optimization itself is almost instant, but what takes time is the first part, identifying the scope of work. So identifying the process, the pipelines, the right equipment to insulate. That's the time-consuming part.
Okay, thank you very much. We received another new questions. So I will take this one to you, Adrian. Do we have high-level cost saving up against each insulation materials through process heat and pipe diameter? If so, can this be shared?
Yes, we have standard tables for this, so we can share the cost saving tables for this.
Okay, thank you. The next one, some of the insulation are reusable example aerogel, and some are not. However, in reality, it's not always reused. Is this taken in consideration in your calculation?
To the degree that the operator agrees. So as I mentioned, this is a tight collaboration with the operators and the process and the installation discipline on the operator side. And every operator have a slightly different experience. As we know, mineral wool, cellular glass, many material will fall apart if you try to reuse them. And even the reusable materials of aerogels are not easy to reuse because you still have the dust handling issue. You have all the logistics with all the different sheets coming off and how to sort it and put it on right again. And most of the time we assume it's not reused because most of the time it isn't. But if the plant has operating system for this, we can take it into consideration. This goes into the lifetime assumption in the calculation. So we factor this into the lifetime assumption of the calculation.
Okay, thank you very much, Adrian. The next one, good morning, my name is Paula. In the material list, mineral wool is missing. Why?
Can you repeat?
In the material list, mineral wool is missing. Why?
Because on this case, in a lot of chemicals in South Korea, they're not using mineral wool in the processing plants very much. They're using perlite, which is the Asian equivalent. It looks and feels like a gypsum board almost. It's like a rigid shell. It works kind of the same way as cellular glass, but it's different. We can do these calculations for any material, so we are not bound by using material A or B. We can calculate optimal thickness for mineral wool, for aerogel, for perlite, for cellular glass, whatever material we together with the client agree is most suitable, we can optimize. It's a general principle, yeah.
Yeah, okay, thank you. The next question we received, can this recorded webinar also be sent out for us to show our business partners? Yes, of course, the webinar is recorded. It's recording right now, and after the webinars, we will upload this video on our company YouTube platform, and we will share the exclusive link to all of you. So you can rewatch this webinar, or you can send it out to any party you would like. Okay, the last question, at least from my side. Adrian, this one goes to you. What's the current focus from a regulating bodies, like a government regulator, in respect to the CO2 emission mechanism and the cost for emission to be acquired by any industrial process facility?
So historically, it's been quite cheap to emit CO2, even when you pay for the quota. When the system started, there was to some degree an abundance of quotas, and it was quite simple for Western countries to buy quotas from poorer countries like Africa, which didn't use their own quotas. What happens is that every year, every time period, the number of quotas is reduced gradually all the time. And we've seen a tightening in this market, as I showed in one of the intro slides. The prices are on the rise for CO2 quotas. I talked with an operator on a refinery in Norway, where they actually replied that the CO2 cost was the main cost driver in terms of heat loss, not the fuel consumption, the CO2 cost. And I think this is and will to a greater extent be the case for many operators going forward as well, as the quotas is reduced year after year, and the prices for the quotas most likely will increase as a result of it.
Okay, thank you. We received another question from the audience. Hi, can you explain how the US dollars values are assigned to CO2 emissions in the calculations?
Using the CO2 quota emission price. So CO2 is actually traded today like any other commodity, like electricity or fuel. So operators in, especially in the Western countries, which adhere to emission policies set up by the government, actually pay taxes on CO2 emission. So an operator in Norway or Germany or France, etc., who consume a unit of fuel and emit a specific tonnage of CO2 actually have to pay a CO2 tax on that. So it actually comes down to the bottom line on the company. And you can Google these prices quite easily. They are traded on a number of exchanges. Some countries have additional taxes on CO2 that come on top of it. So CO2 is actually quite simple to translate into dollars.
Okay, thank you very much, Adrian. I see we don't have any other questions. So yeah, in general, thank you everyone for joining us for this webinar today. For all remaining questions that you would like to share with us after the webinar, don't hesitate to contact us directly. And again, dear audience, thank you again for your engagement and for your time, Adrian. Really interesting presentation. Stay with us in the future webinar. We will publish the link to the recording of this webinar shortly. Take care and enjoy the rest of your week. Thank you very much.